So for this video, we're going to talk about double integrals over general regions, so not just rectangular regions. So there are two types of regions to look at. The textbook calls them type 1 and type 2. So type 1 is we have a region that lies between two horizontal lines. Now that could be actual horizontal lines, as in the first picture here. Or maybe one horizontal line and one value of x, or between two values of x, or something like that. Or type 2 is where we're between two horizontal lines, and so these are figures 5.13 and 5.14 from the text reproduced here. So type 1 regions can be described in this type of set where x is between a and b and y is between two functions of x. And in type 2 regions, x is between two functions of y and y is between two values. So to integrate a function that's continuous on a region of type 1, right, what are we going to do? So think about that for a second, and then I shall write it, okay? Well, you should pause the video so we don't actually waste time thinking, but not that thinking's a waste of time. Okay, so we're going to have the integral from a to b. Now we're going to want to integrate with over y first. So y goes between these two functions of x. And for a function continuous on a region of type 2, of course, well, then we're going to integrate with respect to x first. Now, I'm not interested in us memorizing what type of region we have, although I know the book does mention it. More about sort of, you know, thinking about when thinking each time you integrate, you know, which variable do I want to integrate over? And of course, a region sometimes can be split into two separate regions, D1 and D2, that may be of different types. And then, you know, it might be advantageous to integrate separately over those regions and combine. So this is similar to what we do when we're integrating in Calc 1, where we have split up our intervals sometimes into subintervals. Okay, let's look at examples, because examples, you know, usually help us the most. So for our first example, we're integrating the function e to x divided by y, and our region is given to us explicitly, so we don't really need to draw it unless you are dying to. But for this one, it's pretty clear what we need to compute. We're computing the integral from 1 to 2 and from y to y cubed, since x is the one that's written in terms of functions. We're integrating with respect to x first. And when we do that, of course, y is a constant. So again, implicitly, we're thinking about this. So we're doing this one first, the inner one, and we're going to get y e to the x over y evaluated at the endpoints, dy. So that's going to give us the integral of y times e to the y squared minus y times e to the 1. Integrating that, the antiderivative of y e to the y squared, you could use a u substitution if needed, is just going to be 1/2 e to the y squared, and here we're just going to get a negative 1/2 y squared e to the 1. And again, we're going to evaluate those at the limits as usual. So I'm going to get 1/2 e to the 2 squared minus 1/2 times 2 squared e to the 1 minus 1/2 e to the 1 squared minus 1/2 times 1 squared e to the 1. And when all the dust settles, I'm going to get 1/2 e to the 4 minus 2 e to the 1. And that's the answer. Now for our second integral, we're going to integrate our function, but our region of integration here is a triangle with vertices 0, 3, 1, 1, and 5, 3, which I've taken the liberty of sketching, so to speak. And now we need to find the equations for the lines that are forming the triangle using algebra. And so there's two ways to look at this. Well, the top is hopefully clearly, this is going to be y is equal to 3. And this one is going to be y is equal to negative 2x plus 3, I believe. And this guy is y equals 1/2 x plus 1/2. So let's think about this now. How do we want to integrate? So there's two possibilities. If we want to integrate this as functions of x, we want to integrate as functions of x, right? We need to break the region, and we need to break D into two regions, right? Why is that? Well, if you look at what happens, so let me use the bright magenta one here, right at this point, our y range changes. So D1 is going to be the set of all x, y, and that happens when x is equal to 1. So between 0 and 1, y is going to be between negative 2x plus 3 and 3. And for region 2, x is going to be between 1 and 5. And y is going to be between 1/2 x plus 1/2 and 3. And so in this case, what are we going to obtain? We're going to obtain that our integral is going to be the integral over the first region plus the integral over the second region. Okay, so let's do this then. This is going to give me the integral from 0 to 1. So we're going to integrate with respect to y first. So that's going to be our inner integral. And similarly for the second integral, now x goes from 1 to 5, and y goes from 1/2 x plus 1/2 to 3. 6x squared minus 40y dy dx. Excellent. All right, I'm going to hold off on doing this one, and I'm going to leave this as an exercise. Exercise for you is to complete this, or compute, so you could verify that it works. All right, but however, if we write the lines as functions of y, right, what are we going to do? All right, so when we're looking at integrating with respect to y, right, we're looking sideways. And so if we look sideways, we see that our x ranges between the two lines here. So again, let me pick a different color. Let me go with bright red. Right, so if I'm integrating with respect to here, right? So x goes between those two lines, and y is just ranging between 1 to 3. Let's try that one more time. Okay, so let's do that then. Okay, so the first line, if y is equal to negative 2x plus 3, well then x is going to equal negative 1/2 y plus 3/2. And if y is equal to 1/2 x plus 1/2, then x is going to equal 2y minus 1. And so in this instance, our region D is going to be the set of all points x, y, where x is greater than or equal to negative 1/2 y plus 3/2, and less than or equal to 2y minus 1, and y is ranging between 1 and 3. And so the advantage here is now when I write my integral of my function, I only have one integral. That's the integral from 1 to 3, and from negative 1/2 y plus 3/2 to 2y minus 1 of 6x squared minus 40y. And now I'm integrating with respect to x first, so that's my inner one. So I do this guy first, and I'm left with the integral from 1 to 3. That's 2x cubed minus 40xy, evaluated at the, and you might be saying, well, that was no bargain, because now I have to do this cube thing going. And you're right. Algebraically, it wasn't a bargain. So I get 1/2 y minus 100y squared plus 2 times 2y minus 1 cubed minus 2 times negative 1/2 y plus 3/2 cubed dy. But doing it like this, right, we don't have to, because we can treat this as just one quantity that we're integrating, and similarly here. And so if I look at it that way, my antiderivative is 50y squared minus 100/3 y cubed. Let's see here. Plus, let's see, 1/4 of 1/2, 1/4, 2y minus 1 to the 4th. This is going to become over 4 times 2. This is going to be a plus negative 1/2 y plus 3/2 to the 4th. And then we plug in our limits. So I'm going to get 50 times 3 squared minus 100 over 3 times 3 cubed plus 1/4, 2/6, that's 5 to the 4th, plus negative 3/2 plus 3/2 to the 4th. That one's nice. Minus 50 times 1 squared minus 100/3 times 1 cubed plus 1/4 times 1 to the 4th plus negative 1/2 plus 3/2 to the 4th. And so what is that going to give me? Assuming I didn't make any mistakes when I plugged this into the computer, I got negative 935 over 3. I will leave it to you to check that I didn't screw up. I hope I didn't screw up, but I am only human. And the important thing isn't the number I get, it's understanding how to set these up. And so actually this example leads us into something else that's really important, and that's the ability to change the order of integration, right? Because sometimes changing the order of integration leads to a problem that's much simpler than the original problem. For example, the one we just did, it was somewhat simpler to just have to deal with one integral. To change the order of integration, we just do what we did in that last example, and that's just represent the region in a different way. So for example, if I have this problem here, we cannot do this integral by integrating with respect to y, right? Because we have e to the y cubed. And we would need a y squared in front of the integral to be able to do a u substitution. So we just can't integrate this one with respect to y first. You can check that a u substitution doesn't work. Okay, so let's try reversing the order of integration. Let's try reversing the order of integration. And then after I finish this example, I'll probably call it a video, and then I'll do a short video for the rest. Okay, so to reverse the order of integration, first thing we have to do is sketch the region. which we're going to do by hand because I didn't sketch the region. Okay, so our region that's given is x is between 0 and 3, and y is between x squared and 9. So if I were to sketch the region, what would I have? Okay, so obviously I have part of a parabola, right? So I'm going to have, let me just draw this quickly. All right, so this is my x and y axis, and I have a parabola, right? So my parabola, and so let's say this is y is equal to 9. 1, 2, 3. And so my parabola looks like something like this. And so my region that I'm integrating over is simply this region here. Okay. So this is my region D. Okay, so this line here is y is equal to x squared, but that's going to give me x is equal to the square root of y. We know it's x is equal to the square root of y because it's just the positives. All right, so if we want to reset this up, then we see that x ranges from 0 to square root of y, and y ranges from 0 to 9. All right, now we'll just do this. So now the integral with order reversed is now this guy. So we have the integral from 0 to 9, and now we're integrating with respect to x first, so that comes into the integral, dx dy. Let's see, make sure I copied the integral right, yes. Okay, so when we integrate on the inside, oopsie daisy, we're going to get a 1/4 x to the 4th e to the y cubed. Right now, x is going from 0 to square root of 9. All right, so that's going to give me the integral from 0 to 9 of, well, when I plug in 0, I get 0, but when I plug in square root of y, I get 1/4 y squared e to the y cubed dy. And if we were to do a u substitution, we would see that this is going to give me 1/12 e to the y cubed, and plug in the limits. So I'm going to get 1/12 e to the 9 cubed minus 1/12, which is going to give me 1/12 e to the 729 minus 1, you know, if I'm being fancy. All right, I'm going to stop here, and then we'll talk about applications of double integrals and improper double integrals in the next short video. Have a great day.